Welcome to Aerodynamics in Minutes. Today we are going to find a general solution for exponential models. In my high school, when I first understand this, I was so excited. At the time, on understanding this, I thought I can model and solve any real-world problem. In real world, most of the behaviors of the objects are nonlinear, like exponential, polynomial, or logarithmic. At the end of this video, you will be able to model any exponential functions and you can make your life easier. Before that, let us see what is differentiation. Consider an exponential curve as shown. If I cut a small portion of the curve and zoom in further, good enough to consider the curve as a line. The dy by dx tells us how this small chunk of line varies with respect to x. In other words, it is the slope of that line. And the slope of these chunk of lines will not be equal. Doesn't need to be equal. The second derivative of this curve is how the slopes of the line varies with respect to x. In other words, the slopes of slopes. And we can find the slopes of slopes of slopes for the third derivative, and we can keep on going for high derivatives. Let us take an example. Y is equal to x squared is the curve equation, and the first derivative is 2x, and the second derivative is 2, and of course the third derivative is 0. It is a graph showing how population of fishes varies over time. Let us model this case. If we zoom into the graph, consider two batches of fishes, 169 and 100. Over time, the batch with 169 fishes will reach population of 500 faster than 100 fishes because there are more fishes to reproduce. The rate of change of population is directly proportional to the population. On taking the proportionality outside, dp by t is equal to kp. We can also see that the slope of small chunk of line increases as increase in populations. Since there are more members to reproduce, the change of population over time is equal to constant into population. On moving p and e to the solvable sides and integrating on both sides, we get ln of p is equal to kt plus c. Taking antilog, we get p is equal to e raised to the power kt plus c, where e raised to the power c is constant. Finally, p is equal to c constant into e raised to the power k. Let us take one example to understand it. Initially, there are 10 bacteria. After time is equal to 4, the population grows to 2000. And we need to find at which the bacteria reaches a population of 1 lakh. We know the formula. Population is equal to c into e raised to the power kt. Putting time is equal to 0, we get c is equal to 10. And substituting c is equal to 10, p2 is equal to 2000, and t2 is equal to 4. From the given data, we get k is equal to 1.324 To find the time at which the bacteria population reaches 1 lakh, we substitute all the known variables k, c, and the given population. We get t is equal to 6.9534. And this is the time at which the bacterial population reaches 1 lakh. Now we have successfully modeled an exponential population. Now let us try to model a cup of tea. A graph shown is the experimental data. The temperature versus the temperature of coffee was over time in minutes. As the time goes, the temperature difference between the surroundings and the coffee decreases. The change of coffee temperature with respect to time increases as temperature increases. That is, for lower temperature, the coffee loses less heat, and if the coffee is hot, it loses more heat at the same unit of time. Therefore, we can say that the decrease in coffee temperature with respect to time is directly proportional to the temperature difference between the coffee and the room temperature. To take the proportionality outside, we introduce k. To solve it, dtc by dt is equal to minus k into tc minus ta. On rearranging, we get dt divided by tc minus ta is equal to minus k into dt. On integrating and simplifying, we get tc minus ta is equal to c into e raised to the power minus kt. Let us take a real world example. The table data are experimental values, and the room temperature is equal to 20 degrees Celsius. At time is equal to 10 minutes, the temperature of the coffee is 60 degrees Celsius. And at 40 minutes, the coffee is at 40 degrees Celsius. We will predict the temperature of coffee at the time 60 minutes, and we will compare it with the experimental values. And remember, Tc minus Ta is equal to C into e raised to the power kt. On dividing the two equations, For two timings, C cancel out and K comes to be 0.049, 04 and 462. And substituting the known variables and at time is equal to 10 minutes in the equation, C comes to be 52.255748. Now we know both the constant K and C. And substituting in the equation and time 60 minutes, the temperature of coffee comes to be 30.75567 and the actual value is 30 and the error is just 2.5%. Okay, now let us try to solve human population, and it is one of the exponential example for population. Here you can see the population growth of different countries. Let us try to model India. The reason is the curve is so smooth and better comparably to other countries. Let us take 2 points from the actual data. At the year 1801, there are 1.689 into 10 to the power 8 number of peoples, and at the year 2000, there are 10.56576 into 10 to the power 8 peoples in India. And we will try to find the population at 2019 and compare it with the actual population value. Dividing population 1 and population 2 equations, K comes to be 9.2134 into 10 to the power minus 3. Substituting the year 2000 values and C, we get the constant C is equal to 1.05013. After finding K and C, finding this and solving for year 2019 is very easy, and the predicted population comes to be 12.5870. But the actual population is 13.664 to the power 8 people. And if we plot the equations we modeled on the actual population, we can see that the equation is not that good because the human population is not exponential. It is a complex polynomial curve since the human population is affected by a lot of things. In an upcoming video, we can try to predict the population using a neural network or a regression. You may get bored on solving equations, so I have made a coffee or a hot water equation modeler. All you have to do is click the link in the description and enter the room temperature and the first temperature and its corresponding timing, and similar to second temperature and timing, and select for which you need to solve, either timing or temperature, and enter the value and click submit to solve. And you can download the coffee and population data I have used in the video. Thank you for watching. This is Danish signing off in aerodynamics in minutes. Subscribe for like. See you in the next video. Stay tuned.